Hello everybody, welcome once again to a review of the Spotify genetic algorithm. This algorithm is designed to create playlists, which is an alteration effectively of the knapsack problem. Now specifically this video is the tool proficiency evaluation, and so I'll explain my tool that I'm using and go through how to use it. So the tool I'm using is PyGat. It's probably one of the better genetic algorithm Python modules out there. And I much prefer it to MATLAB because it is fairly simple to use. And we'll get on to that in just a moment. So basically how this will work, and this is the set of tutorials I'm using, one of being the PyGat docs. All we got to do is do a few things. With the help of Jupyter, we can run pretty quickly through this. We import all our modules. We're going to define some specific variables. And for this, I did a lot of random generation for this just demo. So min weight, maximum volume, these are a couple of the specific parameters to these SAC objects. So I wanted to design this to specifically work like a knapsack problem, so I just made the knapsack problem. So I provided three variables. It has a weight, a preference, and a volume for each object. And then we have a function that can make one completely randomly, with the preference being anywhere from 1 to 10, and then the weight ranging from the minimum to the maximum, and same for the volume. These are all defined up here, so if you change those, you can just run this cell, and then you can run one of these cells down here. Right here, we define the number of objects we want. I set it to 100 for the simulation that's done here. And then we define our fitness function. So how this works is this is going to be passed on to our genetic algorithm instance, which will then be used to calculate the fitness of each solution. So how that works is we're going to go through the entire solution, and then if it's greater than 0.5, which we'll get onto that in just a moment, that just makes sure that Python knows, hey, it's 1 or it's 0. And then if it is 1, then we're going to add the volume, the weight, and the preference. And then if either the total weight, the total volume is greater than the maximum total volume or total weight, which is defined up here, then it will return -1. If not, then it will calculate the fitness as the total preference times the sum of basically the percent of the weight used plus the percent of the volume used, which allows us to basically go from 0% to 200%, or double the total preference. And then that's returned as the fitness value. This is then added together to calculate that. Now, for the genetic algorithm instance, we have these parameters preset, but there are a number that you can also use. So we do have some ones that you absolutely have to define. The maximum number of generations, which is defined up here, I set to 4,000 as that seemed pretty close to what was necessary. You can add a stop criterion, like if the fitness remains the same for 1,000 generations or 5,000 generations, then it stops, and then you set the maximum to some ridiculous value. But the number of generations has to be set. The number of parents for the mating does have to be set. And then the parent selection type. I chose rank, but they do have others that you can use. I would suggest checking the docs for those. Then we define our fitness function, which is set up here. You can also define other functions for different states, like during crossover, mutation, start, stop, or each generation. Like maybe you want to generate 1 or 2 extra SAC objects to work with or something. I wouldn't suggest that, but yeah. And then then you get the number of genes, which for this case and in the actual Spotify, it's going to be the length of all the inputs that are being brought in, so the number of inputs. Set the mutation type to inversion because of how this works. We're using the gene space 0, 1, so that's a binary gene space. And with that being the case, the inversion will flip it from 0 to 1. It doesn't have any other choice. we can set the keep parents, which the number of parents is 5. So it will only keep, though, one of those parents. We could adjust num parents up here, for instance, to 2, not 22. We can run that cell, and then we only have to run this cell. This will define all the parameters. This is going to give us an error. This is the output from the actual function running. And then we can run this, it'll calculate stuff and give us the output. So I'm going to pause for just a moment and let this run, because it does take a moment. It's a fairly large problem. So right here is the output. Now, because we have a large number of genes and they're binary in nature, you really can't tell when things are set and unset. This is really useful if you have a smaller or more dynamically rated gene set. Then it outputs the fitness, which tends to level out pretty high up here, and it varies from time to time how that will actually show. Then I just have an extra cell here that'll print out all of our solution stuff. So, for instance, right here is the parameters. This gives you the binary of what all is put in. It gives you the fitness value of all of them, of the highest one, so around 379, 380. Then the index of the best solution. So this is basically like, for instance, I think this one has 20 solutions per generation, and then it just tells you which one has the best fitness out of all of those, which in this case is 0. Sometimes it will change, but normally it's 0 by the time that it goes through everything. Then it outputs all of these guys. I just added a string function that prints the preference, I believe the weight, then the volume. And then it gives you that total weight, which is 100, the total volume, and then the total preference calculated for these. And you can add more and more to this. There are extra things that we could do, like calculate time and so on. But that is how this works. That's how this tool works. Really, even for this, all I have to do is load in the data into a Panda expression, define a few, modify my fitness function, and then I can probably run everything right here, right now. But I hope that you guys have a wonderful rest of your day. I'll see y'all later.